All right, good afternoon, everyone. My name's Ewan Steam. I'm a now alumni of the MSc Environmental Technology course, and I specialised in energy policy with Benny and Phil as my supervisors for my thesis. I'm going to talk to you today about my thesis research, which is called a techno-economic assessment of the viability of utilising electrolysis waste heat for district heating in the UK. So pictured on the left is an electrolyser, on the right is a heat network, trying to integrate the two to make electrolysis cheaper, potentially. Okay, so in terms of agenda, I'll be going over the context, then some existing research gaps, how this led to my own research objectives, my research methodology, starting with the results, a results summary, then the conditions for economic viability of electrolysis plus waste heat cells. So what needs to happen for you to get a profit as an electrolyzer operator by selling waste heat. And then this one is if you want it to be cheaper than other ways to produce hydrogen. And then finally, how you can potentially use my research and model to identify viable projects in the UK, or how you could even enhance the findings through future research. Okay. So in terms of context, there's a lot to unpack here. Utilising electrolyser waste heat for district heating could reduce UK electrolysis costs and stimulate investment in electrolysers. So from the left here, as we probably know, electrolysers electrically produce hydrogen from water, and why people are so interested in them is that they don't produce direct emissions. However, they also, probably as we know, very costly. And relative to SMR, Steam Methane Reformation, they're about 300% of the cost on average in the UK. So it's not very competitive to do electrolysis currently. However, 26% of an electrolyser's electrical input is lost as waste heat at 50 to 70 degrees Celsius, as you can see here. And you could potentially sell this waste heat as a revenue stream, and then you could use that revenue stream to offset the cost of electrolysis, making it cheaper. So heat sales could offset UK electrolysis costs and facilitate the investment we need to achieve a projected 154 terawatts of annual electrolytic production by 2050. Now this figure comes from National Grid ESO and takes the average of their future energy scenarios. So in those energy scenarios, which are seen as the credible pathways for the UK to achieve net zero, the average is we need this much hydrogen to be produced by electrolysis. And we have less than 1 terawatt now. So in the center, we have district heat networks. These, as shown by the diagram, connect building heat users to a central heat source, unlike a boiler you might have in your home, via pipework. And they operate at different temperatures. So 60 degrees Celsius or so for the newer models and 100 degrees Celsius for the older models. And that distinction is very significant because of the difference with this temperature here, but we'll talk about that more later on. Now, heat networks are not very well understood or utilized in the UK. Only 2% of our heat is supplied by heat networks. But the Climate Change Committee is recommending that 18% of our building heat is supplied by heat networks by 2050, which is an 80 terawatt annual demand sink. Which is more than the amount of waste heat that would be available if all of this electrolysis was used. Okay, now the integration opportunity. Electrolysis heat can be captured with water and piped to a heat exchanger. The heat can then be transferred to cool water, piped over a heat network, over from a heat network, as shown by the simple diagram I've got over there, where you've got hot water being piped over and then transferred to cold water from the heat network and then back to the heat network. So heat networks are not very common, as I said, in the UK, but in Denmark, they supply 61% of their heat in buildings using heat networks. And in Denmark, there's a 2.58 gigawatt electrolyzer project pipeline. And then in the Netherlands, 250 megawatt project pipeline, where they are planning to integrate heat networks and electrolyzers. But we still have very little experience of this in the UK. And despite this really strong contextual information that this is viable, you can't really find strong publicly available information telling you what needs to happen for you to do this in a profitable way. Okay, so here are the research gaps. there's strong technical evidence, but significant techno-economic research gaps. So as shown on the left, we have a lot of really nice technical papers which outline how you capture the heat. So you have water pipes that capture the heat from the stack and then bring it to a heat exchanger and transfer that over. So it's quite well understood how to do this from a technical standpoint. Less well understood is how much this costs and how much profit you can extract from it. So there are a number of studies which I've linked here, and you can follow up on if you like, which provide costs across a very few isolated scenarios, but they still don't answer any of these key questions on the right-hand side. So some of these questions are, under which conditions can electrolyzer waste heat be profitably sold to a heat network? So for an example, if I want to build my electrolyzer, how far away can I be from a heat network? How long can the pipeline be before I'm going to lose money if I do this? What if my electricity price is cheaper or more expensive? How is that going to affect this? Those and so many more questions are unanswered, which means that if you're an investor, you probably have no idea whether this is going to work out profitably in your individual circumstances based on the existing information available. And then really importantly, when we talk again about how expensive electrolysis is compared to other types of hydrogen production, is the second question. Can the net revenue make it competitive, say with Steam Methane Reformation? And that's completely unanswered within the existing research. And then temporal analysis. So thinking up to 2050, that key investment timeline, there's not really information going beyond, even 2030 was the only study I found. And then lastly, there's an environmental benefit that's not really been considered, which is if you are delivering heat from clean waste heat to a building and you're not burning natural gas or oil in a lot of cases as well, in some cases, then that's an environmental benefit. How much heating emissions can you displace, and could you even monetize those emissions displacement? Okay, so now my objectives and methodology. So I sought to determine the conditions and extent to which heat sales can improve the economics of alkaline and PEM electrolysis. And I've chosen to focus on measuring changes to the net levelized cost of hydrogen of the electrolyzer, which is the total lifetime discounted cost divided by the total lifetime discounted hydrogen production. And I focus on alkaline and PEM because they represent 97% of the announced project pipeline in Europe from 2020 to 2040. So they're the most relevant. And then I've decided to accommodate wide-ranging sensitivities to kind of clarify a lot of those questions I showed you on the previous slide about conditions for viability. And then lastly, I've decided to focus on calculating, determining situations where electrolysis plus heat cells is cheaper or the same price as steam methane reformation plus carbon capture and storage, which is the main low carbon competitor for hydrogen production in the UK, but not emissions free, as is the potential for electrolysis. Okay, so methodology. I've calculated the costs and benefits of electrolyzer waste heat sales by developing a sensitivity analysis enabled model, and I've given the model a name, as you can see at the top there. Looking at the left-hand side, analysis was centered on calculating what I've called the new levelized cost of hydrogen, summing the following four parts underneath. So the levelized cost of hydrogen is just the cost of producing hydrogen per unit of output of the electrolyzer. And then the levelized cost of waste heat is the cost of delivering each megawatt hour of heat to the heat network. And then the levelized cost of heat revenue is a negative cost cash flow, and it is the cost, the amount of revenue you get from selling the heat divided by the amount of heat that you get during the lifetime of the electrolyzer. And then the last one, the levelized cost of abated carbon. This is also a negative cost, which can be set to zero if you don't want to consider this as an actual business expense. It assumes that each megawatt hour of heat delivered displaces natural gas supplied heat, and then it multiplies that heat abatement by DESNZ's social value of carbon, so the Department of Energy net zero, security and net zero. So looking to the right of the slide, this is just a screen capture from my Excel model, and I had what I called my dashboard sheet, where you have 1 to 23 different variables which have an influence on these different factors that go into producing the NaCOH. And you can select between 3 and 43 different values, and that will trigger calculations throughout the workbook. And then I also have some VBA toggles, so you can select some preset scenarios, which I'll be talking about in a minute. Okay, so in terms of methodology, I focus my economic analysis only on these parts. So everything from the electrolyzer, the heat exchanger, the heat capture system and transmission system, the pipelines. But when you get to the energy substation of a heat network, that part onwards I don't include in my analysis. So these, to the right-hand side, are the key sort of data sources I used for my modeling. And the first was BASE 2021. So they did a major study on hydrogen production costs and efficiency values for alkaline and PEM electrolyzers up to 2050. And they used real GBP 2020 pricing, which I also used in my study. They have low, medium, and high values, which enables me to form part of my sensitivity testing as well. And then all of the fuel prices and value of carbon data I got from DESNZ. And then Van der Roos et al. 2023 did a study on the levelized cost of capturing and transmitting waste heat from an electrolyzer heat network. And I've used that to linearly extend or descend according to electrolyzer size. Their size was 2.5 megawatts. And then lastly, DEC, so that's the former Department of Energy and Climate Change of the UK, which did a massive study on district heat network costs. Okay, now results. So in summary, yes, heat sales can reduce net levelized cost of hydrogen, but they only unlock cost competitive electrolysis in combination with low cost electricity use. So you're looking here at a table summary of some of the key scenarios I investigated in my research. And this table is showing the average results across alkaline and PEM electrolyzers. And I've also used the average results for all of the plant commissioning years between 20 and 2050. So the 2020 commissioning year, PEM plant, 2025, 2030, and so on, up to 2050, both data sets all averaged. So I had my first scenario, which is baseline, and I tried to make this a typical electrolyzer condition. So it's a grid-connected electrolyzer, which most are, and it doesn't have heat cells. This is the baseline, or counterfactual, if you will. And this is set at 10 megawatts with average cost and efficiencies drawing directly from the BASE study. And it uses the average grid electricity price forecast from DESNZ and has an 85% load factor to allow time for downtime maintenance. And this yields a £6.80 per kilogram average figure for the levelized cost of hydrogen between 2020 to 2050, which shows that unsupported grid electrolysis remains very costly and will not become cheaper. And not included on the slide, the price for the 2050 years was £5.70. So it's still far more expensive than today's present cost of SMR plus CCS. Okay, so next is central, which is baseline plus heat cells. So what that means is I've kept everything the same from the previous scenario. I've just added the heat cell system. And this part's really important because pipeline distance and cost affects everything. It's a 200-meter pipeline distance and average cost of the pipeline from DEC. And this yields a 15% average change on the baseline LCOH when you're selling 100% of your heat annually. If you can only sell 20% of your heat, you can break even. And according to your capacity of your electrolyzer, it has a very large bearing on how far you can site from the district heat network. So if it's a 1 megawatt, you can only be 200 meters away. Otherwise, you're going to be losing money. But if you're up to 100 megawatts, you can be 25 kilometers. And these are based on average pipeline costs. So if we use lower or higher values, which there are those values available, then the distance will become lower or larger. So it shows that under typical conditions, there's a high margin for viability, but it's not competitive and probably won't ever be with SMR plus CCS. And then just to clarify an interesting point, central plus heat pump adds a heat pump. And it shows that it's completely non-viable because it's 6% more expensive than if we didn't engage in heat sales at all, even at 200-meter pipeline distance. So we only want to integrate with newer district heat networks because they have a flow temperature that's aligned with the waste heat temperature of an electrolyzer. And then here we come into examples where we have cost competitive electrolysis. So here, central plus curtailed wind, I've replaced the grid electricity price with the price of curtailed wind and assumed the load factor of curtailed wind too. So imagining a condition where an electrolyzer is supplied only by the curtailed electricity of a wind farm. And here we get an 80% drop on the £6.80 figure, which is cost competitive with SMR plus CCS. However, the conditions are tighter. You'd have to sell 60% to achieve that cost competitive price annually, not 20%. And as you can see, the viable pipeline distance greatly decreases. And that's due to the load factor. If you send less heat through the pipeline, your costs are shared across a low amount of heat. And then it's a similar story underneath. This is a scenario where we have a co-ownership arrangement with an offshore wind farm and electrolyzer. So you're imagining the owner has both entities, and the cost of electricity becomes the levelized cost of the offshore wind farm and the load factor of the offshore wind farm, and that becomes 70% cheaper than this, which makes it cost competitive with this, SMR plus CCS. You need to sell more heat than if you had a grid-connected electrolyzer, but it's higher margin for viability than the curtailed wind case. Okay, so to go into conditions for viability in a bit more detail. Firstly, increasing electrolyzer size is one way to extend viable pipeline length to unlock further integration sites. So to explain, pipeline costs are determined by terrain, by building materials, and cost of labor. They are not closely related to how big the electrolyzer is. So you could build a bigger electrolyzer and the pipeline costs might be the same, in which case you could send that heat a far greater distance. And that is very significant because we can probably guess that if you have to build an electrolyzer in an urban area where heat networks are located, it's more costly and there's less land available. But if we build up our electrolyzer to a larger scale, it can go to a much further distance from the electrolyzer. It might even be able to be built in an industrial cluster if the capacity is large enough. You can also see some of the variation in pipeline length according to the cost of the pipeline. So this is the lowest cost value I found from this source, and these are the range values from this source. And you can see that there's quite a big range, but with a 0.2 kilometer average from 1 megawatt extending to this range, 100 megawatts, 17 to 100 kilometers, but 20 kilometer average. Okay. The next condition for viability is to avoid utilization of heat pumps and ensure demand for at least 20% of deliverable heat annually. So as shown on the left with this percentage change here, if you add a heat pump, then it will be more expensive than if you sold heat, than if you didn't sell heat. So there's no point to doing it. And what this means for the UK is that given, as shown by this chart down here, the 2% of heat supplied to buildings in the UK from heat networks are all from first and third generation heat network systems. And we can't really integrate with any of these because the heat temperature they require is higher than the temperature that the electrolyzer provides unless you use a heat pump, and heat pumps are not cost effective. However, the Climate Change Committee, as I mentioned a few slides back, is anticipating we could have 18% of our heat delivered through heat networks by 2050, and this newer build-out will all be fourth and fifth generation systems. So we could have this 16% block of future heat supplied to buildings in the UK connected with an electrolyzer. And then on the right side, ensure a minimum of 20% of deliverable heat is sold. You can see this diagram to the bottom right. As you reduce the amount of heat delivered, your amount of profit you can extract decreases. So 20% here, it's now above the baseline. So you'd be losing money, but on this side, you're gaining money from doing this. Okay, but how can we make electrolysis cost competitive? So we need to pursue low-cost electricity procurement alongside heat sales. This chart on the right of the slide is showing average levelized cost of hydrogen, so without heat sales, and new levelized cost of hydrogen, so with heat sales, across the two electrolyzer technologies and all the commissioning year plants relative to SMR plus CCS on the left. Now, for the central scenario, without heat sales, it's 196% of the price of SMR plus CCS, so not cost competitive. Add heat sales, it's still 148% more costly than SMR plus CCS. But this third set of bars here, if we just change one thing, which is we use curtailed wind electricity price, not grid supplied electricity price, then the cost comes down to 70% below SMR plus CCS without heat sales, and then it falls negative with heat sales. So that shows you just how much bearing electricity price has on electrolysis, and it actually represents 90% of the cost of production in a lot of cases. And then a more plausible scenario is where we use the load factor of curtailed wind as well as the price of curtailed wind, and you can see that it's almost parallel with SMR plus CCS without heat sales in blue, but then green with heat sales, it's 48% below. And then the co-ownership scenario, this probably represents an even more plausible scenario in that we might have a co-ownership across the two entities rather than just using curtailed wind. However, you can see that it's £3.10 per kilogram, which is more than SMR plus CCS without heat sales. The electricity price is doing most of the work in getting the price down, but you need heat sales to make it cost competitive. Okay. Further conditions is a greater requirement for proportion of annual heat sold if you're using those low-cost electricity procurement scenarios. So the issue is that as you lower the load factor, which you inevitably have to do if you're using only variable renewable electricity like wind or solar, then your pipeline costs are going to be levelized across an increasingly smaller amount of heat volume. So that means you must sell more of that heat to break even. So that would mean that you'd have to site somewhere where you can be guaranteed that there's greater demand for your heat than if you were doing grid electrolysis. And that's what this graph is showing on the right. So our not competitive central case, which is grid electrolysis plus heat sales, you have to sell 20% to get profit, but you're still going to be not competitive. To be competitive for these cases, using curtailed wind or an offshore wind farm that's dedicated and co-owned, you have to sell 30%. And then here it's basically the same story. The viable pipeline length decreases due to reduced load factor. So if you have a variable renewable connected electrolyzer, then you're going to have a lower load factor because wind and solar don't operate all the time. And what this does is reduce the viable pipeline distance. So you can see for the central case, which is not competitive, we could have up to 25 kilometers at 100 megawatts, but it's only 5.5 for the curtailed case and 17 for the offshore wind farm co-ownership situation. So again, you want to prioritize low-cost electricity procurement, but you have to guarantee a higher volume of your heat can be sold annually, and you have to be closer to the heat network, which can be challenging if you're using, say, an offshore wind farm and you want to site closer to an urban area if there's a long distance between those two places. Okay. Now some non-relevant factors for cost competitive electrolysis and heat sales. So interestingly, CapEx, OpEx, and the borrowing rate or cost of capital have very limited influence. And that's interesting because a lot of the policy initiatives I've looked at subsidizing the CapEx of electrolyzers, for example, such as the Net Zero Hydrogen Fund, which offsets the price by 30% if you're using clean electricity. But as you can see, lowering the CapEx doesn't have much of an influence because electricity is the most significant factor for the price of electrolysis. So again, 148%, even with heat sales, of the price of SMR plus CCS. But for this case, if we lower the CapEx and OpEx to the lowest values that BEIS has, then you're still 143% of this price. If you use a 3% discount rate, which is going to be unheard of in the electrolysis sector, given it's a new industry, and then heat networks have very limited experience in the UK, then you only reduce it to 135% of this price, and then 130% if you combine. So to reinforce that point, these factors will help, but it's electricity price that is most significant. And then heat cells can take you over the margin to make you cost competitive in a lot more situations than if you just drop the price of electricity. Okay, quantifying the carbon abatement of building heating. So CO2 abatement using waste heat for heating. There's a net abatement with grid electrolysis by 2025 and immediate benefits with clean electricity. So I'll just walk you through these graphs here. This chart here is showing the net lifetime emissions produced by an electrolyzer that is 10 megawatts, that is a grid-connected 10 megawatt electrolyzer running at 85% load factor during its lifetime. So these are all the commissioning years that I studied. For the 2020 year, it's actually producing more emissions during its lifetime than it's displacing if it sells its waste heat. And that's because of the carbon intensity of the UK grid, which is captured very significantly by a 2020 year plan. But according to DESNZ's projections for the decarbonisation of UK electricity, you can see from 2025 onwards, there's less influence of carbon intensity of electricity coming to 2050. And from 2030 onwards, you're getting a much more significant abatement effect because you're displacing natural gas from heating. Okay, and on the right side of the slide, you have a case where you just use clean electricity immediately. And you can see that from the 2020 plant, you're getting 140,000 tons of CO2 equivalent displaced from heating from the get-go. And the way during its lifetime. And the way I have calculated this is assuming that 1 megawatt hour of waste heat displaces 1.1 megawatt hour of natural gas that would otherwise be combusted with a 90% boiler efficiency. And the reason I've used natural gas as the counterfactual is that it's used to heat 83% of homes, but more than 90% of heat networks in the UK are operated using natural gas. Now, interestingly, you'll notice that it's 140,000 lifetime tons of CO2 displaced for the 2020 plan, and it falls to 107,000 in 2050. And the reason is that we have projections that the electrical conversion efficiency of electrolyzers will improve over the coming decades. So the proportion of your electricity that's lost as waste heat will become less and less in coming years. So you're going to be able to sell less waste heat depending on your rated capacity and your load factor. Okay, how could we monetize the CO2 abatement using waste heat? So there are significant benefits for non-grid supplied electrolyzers only. So this chart here is showing average new levelized cost of hydrogen without in green and with in blue monetization of abated heating emissions according to DESNZ's average social value of carbon relative to SMR plus CCS. So the social value of carbon is a societal environmental pound value figure that DESNZ applies to every ton of CO2 equivalent emitted annually, but it's not covered by the emissions trading scheme. So you can see that for the grid supplied electrolyzer with heat cells, adding the social value of carbon just reduces the average cost by 4% during the lifetime, across the average of both plants and all the commissioning years because of the high carbon intensity of the grid during the 2020s. But if we take our non-grid supplied electricity cases on the right-hand side, if we're using curtailed electricity and keeping that everything else the same as the central grid's electricity supplied plus heat cells case, then we reduce our cost by 150%. If we have our curtailed wind electricity price and load factor case, the price comes down by 50%, and then 30% for the co-ownership between an offshore wind farm and electrolyzer case. And what this does is show a way to quantify the additional benefit that you get from using electrolyzer waste heat for heating rather than heating homes through natural gas, which is what we do currently in almost every aspect. Okay, and then finally as next steps. So site identification. we're aiming to publish this research, including the model, in the coming weeks. So all of the results and model itself will be hopefully completely open source. So you'll be able to go into the model and tweak all the sensitivities as you like. Now, what you could do is use these sensitivities and the results you can gain according to your particular electrolyzer operator circumstance to identify places where you can extract profit from siting your electrolyzer near a heat network and selling the waste heat, or even making electrolysis that is cheaper than SMR plus CCS. So on the right-hand side of the chart, of the slide, you have a map of UK heat demand density and a map of current and projected UK heat networks. And these are publicly available sources that I found from DESNIS, and you can download CSV files from those. You could use that to apply them as layers to QGIS, and then you could set boundaries on QGIS or any other kind of GIS system where you filter out places that are not going to be viable. So for example, if I were to do this, I would filter out all non-new heat networks because I know that a heat pump would be required and therefore I'd be not able to extract a profit. In terms of distance, I would use the results from the model according to my particular electrolyzer to prioritize proximity to the heat network to gain the maximum profits, but I'll also recognize the maximum distances according to the pipeline costs that I can achieve for my project and the load factor I know I'm going to have for my electrolyzer and the capacity I know I'm going to have for my electrolyzer. Using the heat demand density map, I could set a distance from that heat demand density, and I would only integrate where there's sufficient demand so that I know that I can sell the minimum amount of heat I need based on the results to break even or to be cheaper than SMR plus CCS. Then if I'm really interested in securing low cost electrolysis that is cost competitive, I would use the set of rules and results from the model to prioritize locations where I can use curtailed electricity and maximize the benefit of heat sales, or where I can have a co-ownership arrangement with an offshore wind farm. In terms of the CO2 abatement effect, I would use it to secure planning permission. Although it's not a viable business expense in the current policy climate, if you're looking to gain approval from a local authority, being able to show not only the CO2 abatement effect of your project, but also quantify that in GBP value, that would be probably quite powerful in getting local authority approval. And then lastly, results enhancement. So there are some areas that could be further improved through study enhancement and extension to bolster the evidence this research provides. So firstly, modeling heat integration of electrolyzers greater than 10 megawatts. So what I've used is a study that is very detailed, but it is based on a 2.5 megawatt case. So what I've done is conservatively extended that upwards to 100 megawatts without considering economies of scale. Now the advantages of that is it's conservative and I'm not making over assumptions. However, future analysis could help by clarifying whether the costs and systems are linearly scalable or whether it could be cheaper for all of those systems if you increase from a small to large electrolyzer. And then the technical analysis of required pipelines. So what I've done is given a cost range by using robust sources. However, I've not provided specific case study examples of how terrain or cost of labor or materials and so on will affect your project and how far you can be sited between an electrolyzer and heat network. So future analysis could clarify those areas by taking a more case study approach to determining how much the pipeline will cost based on different terrains or how much the labor will cost and so on, and then integrating that with the model results. Lastly, techno-economic analysis of electrolyzer waste heat for industry. So the limitation of this study is that it only integrates electrolyzers with heat networks. However, many industrial heat users use heat rated at around 120 degrees Celsius. So if you could potentially utilize electrolyzer waste heat for that industrial heat use, then you wouldn't need to site near urban areas where district heat networks are located. you'd have a much broader demand sink for the heat. So future analysis could confirm the viability of electrolyzer waste heat for industry, and that would be another really useful and important development of this research. Okay, and that's the end of my presentation. Thank you. Q&A.
Can I go first?
Yes.
Is that all right? Yeah. All right. Somebody else got a question. So just to come back to your sort of variation where you use curtailed wind.
Yes.
Is that wind curtailed wind from a single wind farm, or is that some sort of representation of a nationally curtailed wind?
So what I've done is just assume the curtailed wind price,
Okay.
and then the load factor of curtailed wind, which is the average nationally.
Right. So when you say the load factor of curtailed wind, so just to explain what you mean by that.
So I've taken a value from Bayes, which is 25%, is the average load factor for curtailed wind in the UK. And
because I'm not quite clear on what is meant by that, are they is that saying that 25% of nationally of wind is curtailed? Because that's not the case right now. That's for sure.
So their figure is 25%.
Okay.
So from a particular wind farm, across the wind farms they've studied, they found that 25% of the time it's curtailed.
Okay. And that's on a volume basis rather than a sort of time basis. Yeah,
I think it might be on a time basis.
Right, okay.
Yeah.
Okay. Interesting.
Yeah.
Okay. Thank you.
Okay.
I have one. I was interested to see that if you go back to the slide looking at the sensitivities, that the discount rate didn't substantially affect the cost. Yeah, this one. Is that because the cost of electricity is treated as like you're buying it every year?
Yeah, it's a variable cost.
Right. Okay.
Yeah. So the electricity price is not affected by the discount rate.
Well, strictly it is, but the effect is spread over many years, so you expect a lot less.
Yeah.
We're trying to say selling waste heat has more impact than offering a lower discount rate or a low capex. You might as well exploit waste heat revenue from waste heat to reduce the cost of electricity packaging.
Or combine them, but recognizing that just reducing the upfront capex of the electrolyzer stack and the facility is not going to be sufficient to make it cost effective with an example like SMR plus CCS. Yeah.
Of course, that rather assumes that SMR plus CCS number is correct, doesn't it? Because I mean, it's we haven't got one, have we? So we don't actually know whether that number is correct, do we?
So according to that same study, SMR was £2 a kilowatt. So if you like, you could compare it to SMR instead. I kind of wonder which one would be correct to focus on, but within all the future energy scenarios I looked at, they didn't have any SMR because they're trying to not do it because of the emissions associated. So I thought this would be the main candidate for comparison, in 1%. But yeah, it was £2 per gram, so with carbon price included, which is not so different. Yeah.
I've got one more question. Sorry, you were about. You go for you.
But thank you for your talk. It's really interesting. I was just wondering about the SMR and the CCS costs. Is that do you think that was likely going to change the next few years, and do you think that would affect the viability? Because I know you said the kind of electronic.
I do think it will start to go up because of the carbon price getting higher. Yeah, but not enough to make it comparable to electrolysis without some kind of support, either substantially from policy, from lower electricity cost, or from waste heat. Yeah.
If I can add something to that, as SMR, it's quite dependent upon the cost of natural gas. obviously it's because it's coming from natural gas. So the past like year or two has seen SMR prices like skyrocket. So it depends whether you think that's going to continue for the next sort of 5 years.
Do you think factoring in the sort of current price, do you think that 2.3 figure is based on
I think that was 2020. Is it the hydrogen production?
pre-Ukraine? Yeah.
Pre-Ukraine. So yeah, I think it might have gone up.
Higher.
recently.
Oh.
But I don't know if it'll stay that level.
Yeah, but if we knew what the current
Right.
price of gas would be, we wouldn't be sat here, we'd probably making millions on gas futures, wouldn't we? Yeah. I've got one more question. Is that all right? So your electrolyzer size, I think you was varying between what 1 megawatt and was it 20 megawatts, something like that?
100.
I think 100 megawatts. How big is current sort of like electrolyzers? You know, is there a 100 megawatt electrolyzer out there?
There are.
Okay, right.
I thought that would be a useful add-on to include
Yeah.
post hand-in actually, because
It's too late now.
yeah, I know. But,
Right, going in the
I've read a lot about the interest in building bigger and bigger electrolyzers because then we can lock in economies of scale benefit. So I thought it'd be interesting to try and model that. And it doesn't, according to the linearly increased prices of all the systems that I've used, it doesn't affect the levelized cost of hydrogen that much, but it does allow you to distribute the pipeline costs across more volume of heat, so you can be further away from the heat network.
Just for the sake of it, what is the biggest sort of like commercial electrolyzer you can buy or get built for you, roughly?
I was listening to a podcast the other day, and they said like 200 megawatts.
Okay, right. Okay.
In Scandinavia somewhere. Yeah.
Yeah. Cool. Thanks.
Any questions?
Just to add on to that, so what's like the current sizes that the UK specifically is looking at for electrolyzers?
So the central value that Bayes gives is 10 megawatts.
Okay.
So we can assume that most electrolyzers are 10 megawatts or less. Yeah.
But presumably, if any of the sort of Herculean sort of estimates for the amount of hydrogen we're going to need by 2050 are right, then we're going to need a lot of 10 megawatt electrolyzers. Yeah.
The electricity system operator thinks more than 120 or 100. I think it was 154 terawatt hours average across their net zero scenarios. The only one they don't have high amounts of electrolytic hydrogen is the scenario where we call falling short, where we fail to reach net zero. So hopefully we will have that hydrogen from electrolysis.
Yeah.
I don't know if you explore the scenario where if we do have that hydrogen from electrolysis from the 154, is the waste heat sufficient to meet the UK's demand for heats, for instance? No, it's still very small.
No. So if I go back, because the electrical conversion efficiency is improving, maybe we can say it's 18%. Rather than 26%. 18% of that is less than this. Right?
So yeah, it's 80 terawatt.
80 terawatt hours is 18% of the amount of heat we use in buildings, or will use in buildings in 2050. So it's just a massive amount of heat that we use every year. So I don't think this is going to be the main way that we deliver heat in the UK ever. There will be heat pumps, probably.
Okay.
But this can help, because if we have this waste heat that's being produced anyway, and we need to make the hydrogen cheaper for all the other reasons that we need hydrogen, then we can reduce the amount of electricity that we mine. And that will all be peak electricity demand as well. Demand.
Any other questions?
Very good.
Can we clap for Chris?